All right, so we saw in the last section we could reduce carbonyls into alcohols. So we can also do the opposite and oxidize alcohols into carbonyls. So we can do this in a bunch of different ways, but what the product we're going to end up with depends on our starting alcohol. So for example, if the starting alcohol is a primary alcohol, we could first oxidize it. And this bracket and this O in the bracket stands for oxidation. So we can first oxidize it into an aldehyde, and then we could further oxidize it into a carboxylic acid. How far you're going to go depends on which reagent you have. The reason that we can oxidize this all the way to a carboxylic acid is because we have two hydrogens here that we can get rid of and basically oxidize. If we have a secondary alcohol, such as this one right here, now we only have one hydrogen that we can oxidize away. And so we can convert this into a ketone, but we cannot oxidize any further. And then finally, if we have a tertiary alcohol, we cannot oxidize that at all, at least through any of the methods that we're going to learn. Obviously, there's methods out there. There's a whole bunch of different ways to oxidize compounds, and it depends on kind of what you want to get, and as well as the experimental conditions. The most commonly learned one is the Jones oxidation. And this one will go all the way to the carboxylic acid if possible. So if you have a primary alcohol, this will go all the way to the carboxylic acid. So for example, here, there's different reagents that you can use, but they all essentially do the same thing. It's just there's an activated kind of intermediate that's used. So you can either see this through as dichromate, sodium dichromate in acidic conditions. That'll get you all the way to a carboxylic acid. Or the other reagent that you'll commonly see used is CrO3 in acidic conditions with some acetone as the solvent, either written out as acetone or the word acetone. Either way, this will also oxidize. It's the same reaction. If you have a primary alcohol, you go all the way to a carboxylic acid. If you have a secondary alcohol, you'll stop at the ketone. If you have a tertiary alcohol, this isn't going to work at all. If you want to stop at an aldehyde for a primary alcohol, you have a number of choices to use as reagents here as well. You can use PCC. And this is generally done in dichloromethane. And then here you stop at the aldehyde. PCC is this compound right here. So it's a protonated pyrimidine, and then CrO3Cl with a negative charge on the chromium. Again, that stops as the aldehyde. There's other reagents you can use as well. DMP, this stands for Des-Martin pyrimidine. Not really sure how to pronounce that. This is another really pretty complex looking compound. So in this case, we have an iodine right here. And this iodine is attached to 3 acetates. Sorry, forgot the oxygens there. Again, this is going to go ahead and stop at the aldehyde. You can do what's known as a Swern oxidation. Which uses DMSO and then COCl2, followed up by some base. And again, this is also going to stop at the aldehyde. This one right here, it just basically creates a very electrophilic compound that your reaction can then go through. You'll take a look at the specific mechanisms through the work along, but the specific mechanisms aren't quite as important as knowing the general idea. So we'll just call this a generic mechanism. And all the reactions above work through this general mechanism. There are some slight variations, of course, but generally they're the same thing. So what we have here is we have some kind of alcohol, obviously, that we're going to oxidize. And then in addition to that, we have our oxidant, which I'm just going to call OX for oxidant. And generally what occurs here is the alcohol attacks your oxidant. There might be like an intramolecular reaction that occurs here as well. Like maybe you have a double bond O and one of the pi bonds gets kicked off. Depends on the specific reagent that you have. After that, generally you have some kind of proton transfer occur. So what we're doing is just going to get rid of this H. Sometimes you'll see that drawn out. Sometimes you'll see just PT transfer written. And depending where you look at the mechanism, they might not even show that. All right, so the main point that we've done here is we've attached this oxidant onto this oxygen. And this oxidant is also a very good leaving group, right? So that's that first step, is to attach the oxidant, which is also a good leaving group, onto the oxygen from your alcohol. And then in step 2, what's going to occur is basically approximately an E2 reaction. So think back to first semester Chem 101. In an E2 reaction, you have some kind of leaving group, you have some kind of beta hydrogen, and then you have some kind of base. The base attacks the beta hydrogen, the carbon hydrogen bond becomes a pi bond, and then the leaving group leaves, right? That's your general mechanism for an E2 reaction. Here we're going to have a very similar thing occur. So we have that hydrogen that we can eliminate out. We have our base come in, it picks up that hydrogen. Now this carbon-hydrogen bond becomes a pi bond. The difference, of course, here is that becomes a carbon-oxygen pi bond instead of a carbon-carbon pi bond. And then our oxidant, which is also a good leaving group, goes ahead and just leaves. And then if you think about what occurred there, you formed your oxidized compound, right? Your carbonyl. Depending on which reagent you use, it'll either stop at this aldehyde or it might go further into the carboxylic acid. If you're going to go further to the carboxylic acid, there's kind of a minor step that you want to keep track of. So let's say we have an aldehyde and we're going to oxidize further to a carboxylic acid. The key step in this one to make it kind of make sense is to have a water molecule attack your carbonyl. And then for a proton transfer to occur. And then what you get there is called a diol, right? We have 2 alcohols attached to here. And then we're going to attach our oxidant to one of these alcohols and then do some kind of proton transfer. Right, so we've got our alcohol attached to some kind of good leaving group or our oxidant. And then, of course, we have this beta hydrogen essentially, and our base comes in, picks up the hydrogen. The carbon-hydrogen bond becomes a pi bond. And the leaving group or your oxidant goes ahead and leaves. And then, boom, you've oxidized all the way to a carboxylic acid. And again, which specific oxidant you use depends more on experimental conditions. The main thing that you want to keep in mind is that the Jones oxidation will go all the way to a carboxylic acid. All the other ones that we learned will stop at an aldehyde. Of course, if you have a secondary alcohol, you will only go to the ketone. And if you have a tertiary alcohol, no reaction occurs.